All right. So my plan for today is to at least start inhibitors. We'll probably not be able to finish till at least Wednesday or Friday of next week, just because there's a lot of inhibitor stuff. There is a Cheminar today at 2 o'clock in the Science Auditorium. There is a biology seminar on Tuesday at 11 a.m. in the Science Auditorium. There's a group quiz today. Reminder that your exam 2 has been bumped forward. It's now October 28th. Not the 25th anymore, it's the 28th. And Chapter 7 homework will be due next Friday, so no homework today. Yes, questions?
Is the seminar actually this Tuesday? I know it's already.
Oh, sorry, next Tuesday. Yeah, next Tuesday.
I was like, okay.
Yeah, no, sorry, next Tuesday. No, it's Dr. Mangoni this time. He's going to be talking next Tuesday. Yeah. Okay. In that case, let's start our discussion of inhibitors. So, inhibitors are defined as any substance that reduces an enzyme's activity to make products by influencing two main things. First, it's going to reduce the binding of the substrate, which we can calculate by looking at the Km of that substance, or that enzyme. And the inhibitor can also reduce an enzyme's activity by influencing the turnover number, which is kcat. So to see if we have an inhibitor in our solution, we examine Km and kcat and see if those are being influenced. Inhibitors can work through a variety of mechanisms. There's two main mechanisms, though, that I care about. First mechanism is an irreversible enzyme inhibitor, otherwise known as inactivators. As the name describes, an inactivator permanently blocks the enzyme's active site. Or modifies, blocks or modifies. So if it permanently blocks or modifies the enzyme active site, it is no longer able to interact with a substrate and can no longer make products. Good, okay. The other big category is going to be reversible. A reversible inhibitor diminishes the enzyme activity by interacting with the active site in a reversible manner. So it doesn't permanently bind to the active site or modify the active site. Often, reversible inhibitors structurally resemble substrates. So I'm going to do my example over here of this. So succinate versus malate. So succinate has this structure. So succinate in the presence of succinate dehydrogenase. Forms a double bond in between the 2 and 3 carbons. However, malate has a similar structure, so it's able to fit into the active site. But it does not react to make a product.
Was I supposed to say malate
This is succinate. This is succinate dehydrogenase, and this is malate in succinate dehydrogenase. Okay, so the same enzyme can react with two different possible ones. This would be considered a substrate. This would be considered an inhibitor because they are going to be competing for the same active site. Side note, what can we tell about the active site if both of those fit into the active site? What type of amino acid is probably in the active site? Polar. What charge would it probably have? Excellent. Good. Just making sure we're all still thinking about that. Right? So if succinate has two negative charges, and malate both has two negative charges, that probably there should be two positive charges in the active site to be able to hold it in place while it does some chemistry. Okay. Good. The other thing about reversible inhibitors is that they affect the catalytic activity without interfering with substrate binding. So, unlike the irreversible, where irreversible permanently modifies the enzyme active site, reversible does not affect the active site in a way that can't be undone. So there's three types of reversible inhibitors. I think so. Let me put it up here. So three reversible inhibitor categories that we're going to walk our way through. One, competitive. Put them in the right order. Two is going to be uncompetitive. And the third category is called mixed/non-competitive. So we're going to walk through each of these three main categories and see what makes an inhibitor fall into one of these categories. Okay? So let's look at competitive first. So a competitive inhibitor competes directly with the substrate. It resembles the substrate. So an example of competitor is the one we just did. This is a competitive inhibition. Succinate versus malate for succinate dehydrogenase. Competes directly with the active site with the normal substrate and physically resembles the substrate. So that would be an example of competitive inhibitor. It specifically binds to the active site so as you see over here with succinate and malate, they both have structural features in common that allows for specific binding. So they both have carboxylic acids that are negatively charged on the terminal ends. The only difference is how far apart they are. So either they're 2 carbons apart or they're just 1 carbon apart. So it's allowing for specific binding in the active site. We'll come back to product inhibition here in a little bit. So just as a definition, and then we'll discuss it more later. Product inhibition is where the product of the enzyme substrate reaction also competes for the enzyme active site. So we'll talk about then that either at the end of class today or most likely on Wednesday. It's also called feedback inhibition. We may have called that in some other classes, where the final product also competes for the original enzyme to turn on and off that cycle. So sometimes called feedback inhibition. Both are true, product inhibition or feedback inhibition. Okay. Everybody got everything in that so far? Good. Bless you. Competitive inhibition, right, we just had over here that resembles the substrate. It could also resemble the transition state. So compounds that mimic the transition state of, the ES, can also act as inhibitors. So my example for that, I'll draw it down here. All right, so there's my substrate. In the presence of an enzyme, it goes through the transition state. This enol form that we looked at, oh gosh, when we first started enzymes. That's one of the examples we looked at, where we go through a transition state through an enol form. A transition state analog means that there is a different compound that looks very similar to this compound that will compete for the active site. What again?
The Eames group.
The transition state analog. No reaction. So this is a compound that exists floating around. And if it interacts with this enzyme, it competes for the same site. And this causes no reaction. Because these two look similar. That they have similar structure. So, transition state analog depends on the inhibitor binding selectively and rapidly. I don't really know where I'll write it over here. So the enzyme binds a molecule that looks like the transition state. And blocks the active site for the original substrate. Okay, so then let's take a look at how this type of competitive inhibitor affects the Michaelis-Menten equation. We'll come back to the graph. I'll work over here, then we'll come to the graph. All right, so if I was going to draw a schematic for a competitive inhibitor, right, enzyme plus substrate, yeah.
So I have a question about that. So
Mhm.
you kind of used it with the transition analog.
Yep.
So if an enzyme is already bound to a substrate in the transition, like how is it allowed to bind something that looks like?
It can't. They're competing for the same site. So either it has bound this, or it bound that. This or that. Right, so either it binds the substrate and goes through a transition state, or it just goes ahead and binds this other thing that looks like step 2. Let me draw my little schematic, maybe that'll help. My flow diagram. Right, that's what we consider our regular. So I could bind S and go this way, or I could bind the inhibitor and get stuck at a transition state analog that makes nothing. So my option is either regular reaction or the inhibitor causes it gets stuck in there and then nothing happens. We're going to call this double arrow big K, little I. Ki. Is a measure of this. The concentration of inhibitor times the concentration of free enzyme divided by the concentration of the enzyme inhibitor combination. And just as a reminder, when we get to an EI state, that's catalytically inactive. So if you see that, it means the reaction has stopped. When I make this EI combination, what happens to the amount of enzyme available to do my top reaction? It goes down. All right, so if I have the inhibitor binding up my active site, what I've done is I've really reduced the amount of enzyme available for substrate reactions. Yeah.
But if it's reversible, doesn't it just go back, so it's not available again? So it's just slow?
Yes. It makes it, the total available is less because even though it's reversible, it can go back. It's still tying up some of the enzyme at all times.
Because when it's going back, it's still going forward.
Right, so even though it goes back to this, if there's enough inhibitor, depending on the ratio of substrate to inhibitor, if there's a lot of inhibitor, it'll choose to go down this path. If there's not enough substrate to force it down this path. Does that make sense? Little Chatelier's principle. Okay. So, let me also, this Ki term is called is the dissociation constant for EI. Okay, so now let's look at how this plays into our original Michaelis-Menten equation. So the Michaelis-Menten equation for competitive inhibition reaction. Must include a term that tells you that there's an inhibitor in there. So our new equation has to include I in some way. So here is our new Michaelis-Menten equation for competitive inhibitors. Who can spot the new term? Alpha. Excellent. Let's figure out what alpha means. Just checking, making sure everybody's conscious. Alpha is equal to 1 plus the concentration of I divided by Ki. So that is our inhibition factor. What would alpha equal if there is no inhibitor? So alpha if alpha equals 1, there's no inhibitor, what happens to my equation? It stays the same, right? Now this is equal to 1, and it's like just a regular Michaelis-Menten equation. So numerically, be thinking about that. What if I have, I guess we'll look at the graph and that'll make more sense. So this is my competitive inhibition graph. I have Vmax as my maximum velocity for the reaction. I have, right, initial velocity on the y-axis. I got substrate concentration on the x-axis. Vmax over 2 is equal to Km. All right, Vmax over 2 is the point at which you're at the concentration that equals Km, which equals Vmax over 2. So let's take a look at our three. If you print it off in black and white, you'll want to use some colors from this point on, just so you can tell them apart. So if I have no inhibitor, this is my original no inhibitor, where alpha equals 1. As I add inhibitor, so I'm increasing inhibitor, alpha goes from 1 for no inhibitor. If I now have a concentration of inhibitor, alpha has to get bigger. And so I'm going to look at alpha equal 2. And so my reaction is now here. What is that telling you about how much, well, that's a bunch of questions. What's it telling you about how quickly the reaction is going forward? It's slowing down some, right? Because it's not nearly as close to Vmax as it used to be. So I can't reach Vmax because I now have two things competing for the active site. Michaelis-Menten constant has gotten bigger because my Vmax over 2 now reaches 2 km, which I mean I now need twice as much substrate as I did before to reach the same maximal velocity, which makes sense. And then if I go up to alpha equal 4, where now I have a lot of inhibitor, I now have to have almost quadruple the amount of substrate to get to the same 1/2 maximal velocity. Because that inhibitor, more inhibitor requires more substrate to get to the same max velocity. Everybody see those points on the graph? All right. Let's point out some other things then. So the presence of I, having an inhibitor in your system, makes the concentration of substrate appear less than what it truly is. And we can see that from the graph, that when we add an inhibitor, we have to, even though you have to add more substrate to get to the same velocity. So if I look at the same concentration of substrate for 3 different examples, no inhibitor, inhibitor, lots of inhibitor, it makes it appear like there's actually less substrate in there because it's reacting much slower than what you would expect with that amount of substrate in there. Okay? And as we just talked about, if you increase the amount of substrate, you can overcome the effects of the inhibitor. So adding more substrate overcomes the effects of having the inhibitor. I have this on. Let's see, I guess I'll write this up here at the top. So for inhibitors, we use a different Michaelis-Menten constant. We use the Km apparent, which Km apparent is equal to alpha times the Michaelis-Menten constant. So looking down here, it's just those two terms together are more appropriately referred to as the apparent Michaelis-Menten constant. Yeah, okay. I'll do that. I'll put it on the next line. Everybody good on those points? Questions? It's a lot of stuff today. And a lot of stuff Wednesday. It's a big chapter. Lots of stuff. Okay. So Ki can be measured for a given reaction. So that you label this for later, you know what this is. This is the competitive inhibitor Line-Weaver-Burke plot. So again, alpha equals 1 plus concentration of I over Ki. A Line-Weaver-Burke plot measures 1 over initial velocity So this should look almost identical to our regular Line-Weaver-Burke plot, with the exception of we got that alpha hanging out in there. So again, I've written this in the equation of a line, so I have y equals mx plus b. So the y-axis has to be 1 over initial velocity, which it is. The 1 over substrate has to be the x-axis, which it is. The slope is given right here, alpha km divided by Vmax. And my y-intercept is 1 over Vmax. Okay. So then let's take a look at the graph and see what happens as I increase the concentration of inhibitor. So as I increase I, and now it's going in this direction, because this is alpha 1, alpha 2, alpha 4. So now I'm going from no inhibitor to lots of inhibitor. I don't know if I can have them both on. Oh, that's pretty good. Okay, so as I increases, what happens to my value for Vmax? Okay, Vmax is right here. Stays the same for all of them, okay? Remember, you're looking at the competitive, okay, so. So as I increases for competitive inhibitor, Vmax remains constant. What happens to my Km apparent, which is the same thing as alpha Km? So it was here. Then with some inhibitor, it goes here. Then with some inhibitor, it goes there. It is increasing because it's the 1 over. So the 1 over value is decreasing, but the actual value is increasing. So, just as a reminder, how do I want to phrase this so it makes the most sense? That's not spelled right. No extra C. So just, we talked about this probably a day or two ago, that the lower the value of the Km, it tells you it's more efficient. So now if I'm moving to a larger value of Km, it's less efficient, which makes sense. Increases with increasing inhibitor, which tells me that my enzyme is not acting as efficiently as it would have been without the inhibitor. Okay. Is there anything else for this part? I guess I'll give an example of a competitive inhibitor. How many people had Dr. Davis for organic? A few? Not very many. Okay. I don't know if Dr. Brennan tells this either. So he might have. So my example of a competitive inhibitor is going to be an example of methanol poisoning. I'm going to finish my story on the back because I didn't leave myself enough space. So methanol by itself would only be mildly toxic, but your liver wants to convert it to formaldehyde, which is super toxic. Blindness, death, not good. But don't worry, ethanol, being structurally similar, competes for the same enzyme's active site, which is similar in the case like when we looked at succinate and malonate. They look very similar. The difference is just that one extra carbon difference. And so the same thing here. Methanol and ethanol are structurally similar, so they can compete for the same active site. So for methanol poisoning, what do you think the patient should do? Drink a ton of alcohol. That's exactly what they do. So if you find yourself in methanol poisoning, you're supposed to drink a ton of alcohol. And it turns out that ethanol is preferentially bound compared to the methanol. So if you drink enough ethanol, you have swamped out the effects of the inhibitor, And the methanol is excreted intact in your urine. So you just pee out the extra. You're probably super drunk and not feeling great, but you're not blind. So I guess that's a trade-off. So that's my competitive inhibitor example. Let's at least look at my uncompetitive. And this one's labeled wrong. Sorry, I must have been copying and pasting. This should be uncompetitive inhibitors. So this is where the inhibitor binds to the enzyme substrate complex, not to the empty active site. So the substrate has to be bound for this one to inhibit. So I'm going to draw another flow chart because I find those useful. And we'll stop after the flow chart. I'll leave you guys hanging. So an uncompetitor, you have to get to the transition state before the inhibitor can bind. Then it makes this new ESI that cannot carry on. Makes no more reaction. Okay, today's quiz is just a few multiple choice questions.